Okay, let's unpack this source stack. We are uh, diving into a realm where the philosophical search for what we call proper science collided, and I mean violently, with a potential energy breakthrough,
Hmm.
one that could, literally change the world. Our sources are dealing with this fundamental, really frustrating challenge of defining what's real, what's revolutionary.
And what's just, pathological.
Exactly. And to illustrate this, they take us straight through the volatile three-decade history of one of the most controversial topics in modern physics, low-energy nuclear reactions,
Better known as cold fusion.
better known as cold fusion.
That's exactly right. And this deep dive is so critical for understanding the mechanics of really scientific failure and then this subsequent resurgence.
Yeah.
We're not just looking at a physics problem here, it's a sociological one. We're comparing this abstract critique of intellectual failure, what a Nobel laureate once called pathological science.
The science of things that aren't so.
That's the one. Comparing that with the hard reality of a strategic risk. The question for us today is really, what's the cost of being wrong? Not just about the physics, but about the whole process of how we investigate things.
So what's the mission today? We have a lot of ground to cover here, from, obscure philosophy all the way to multi-million-dollar NASA programs. What do we owe you, the listener, by the time we finish this deep dive?
Okay, so our mission is, I think, very meticulously structured. First, we really need to spend time dismantling the philosophical and historical labels.
The ones used to just dismiss things.
Exactly. Dismiss revolutionary high-novelty science. We need to show why those labels, well, they often fail when you look back at them.
Okay.
Second, we have to fully review the historical crisis of cold fusion. I mean, the rapid dismissal in 1989 and the lasting reputation trap that it created.
And finally,
We'll analyze the empirical evidence that has forced major institutional players. We're talking the U.S. Department of Energy's ARPA-E. We're talking NASA to commit millions of dollars to rigorously proving a field that was, previously declared impossible. We're looking for that aha moment that bridges the historical failure with the current undeniable strategic need for this.
Okay, let's start at that intellectual battlefield. It begins not with atoms, but with philosophy.
Mhm.
For, centuries, thinkers and scientists have struggled with what's known as the demarcation problem.
Mm-hmm.
How do you definitively, universally, and objectively separate proper science from pseudoscience?
And the sources really emphasize that this search has been, to date, completely fruitless. Historically, this quest consumed some of the greatest minds. You had the logical positivist trying to find some absolute truth.
And that failed.
That failed. Then you had Karl Popper, who offered falsifiability. The idea that a theory is only scientific if you can imagine an experiment that could prove it wrong.
But that proved too strict.
Way too strict. Then came Imre Lakatos, who suggested, well, a progressive research program has to continually generate novel facts.
But if all these rigorous, really smart attempts failed, why? Why does the whole idea of a universal scientific checklist just collapse when you try to apply it?
It collapses because when you look closely at the actual messy day-to-day practices of established fields, the ones everyone agrees are proper science, like chemistry, physics, biology, those practices are, as our sources put it, polyglot in the extreme.
Polyglot, okay.
Yeah, I mean, practicing scientists rarely set out to deliberately follow some universal checklist of properly scientific criteria. They just use what works, and what works might be radically different from one discipline to the next.
So when we say polyglot, are we talking about the fundamental differences in approach? Can you give us a concrete example of that reality?
Oh, sure. Just think about the difference between, say, a high-energy particle physicist and a field biologist.
Okay, two very different worlds.
Totally different. The physicist, working at a super collider, relies on creating these controlled multi-million-dollar environments to detect fleeting subatomic particles that only exist for, a picosecond.
And their data it's not raw.
Not at all. It's generated through these complex computer algorithms that have to remove all the background noise. Now you look at the field biologist, they might be using mass spectrometry and radio collars to study the metabolism of a species in a rainforest.
Right.
The physicist is, in a way, manipulating reality to see something new. The biologist is observing and interpreting an already established, incredibly complex reality.
Both are completely rigorous science.
Absolutely. But their methods, their standards of proof, their acceptable levels of uncertainty are wildly different. A single demarcation rule just can't possibly encompass both of them.
And this inability to clearly define and then recognize profound novelty when it first appears has, massive real-world consequences, especially for true breakthroughs.
It really does. The sources point out that the absence of a satisfactory demarcation scheme is precisely why concepts that were revolutionary and turned out to be correct were so often ignored for decades.
We're talking about the classics here.
The two classic examples, Gregor Mendel's rules of heredity and Alfred Wegener's theory of continental drift.
Mendel's work was published in 1866, but it was basically forgotten until the 20th century. Wegener published his theory in 1912 and he was ridiculed for decades. So why were they classified as premature science?
Well, they both suffered because the scientific community just lacked a conceptual framework to correctly classify that level of profound novelty. Wegener proposed a novel theory that continents move.
Right.
But he also used novel methods. He was drawing on geology, paleontology, climatology in a way that just violated the disciplinary boundaries of the time.
And Mendel.
Same story, different field. Mendel presented a novel theory of discrete units of inheritance. But his data collection methods, counting thousands and thousands of pea plants, were statistically rigorous but conceptually totally foreign to the biologists of his era.
So because their novelty struck at two different facets of accepted science at the same time?
The established practitioners didn't just disagree. They simply couldn't slot the work into their existing framework, so they just discarded it.
That brings us directly to Thomas Kuhn, whose model of scientific change gives us a much better lens for viewing this kind of intellectual dismissal.
Kuhn contrasts the mass majority of scientific work, which he calls normal science, with the very rare scientific revolutions.
And normal science is just puzzle solving.
It's essentially puzzle solving. You accept the long-standing paradigm, the theories, the data, the methods, and you just work within that framework, refining and extending what's already known. A revolution, however, introduces startling novelty in at least one of those three facets.
Okay, so we have the three facets: theory, data, or method. A breakthrough might be novel in just one, but a true revolution is novel in two or even all three.
And that's the key distinction. If the novelty is primarily in theory, like, say, Einstein's relativity, the scientists still trust the empirical data and the experimental methods. If the novelty is primarily in data like the discovery of radioactivity, the existing theories might get strained, but the methods are recognizable. But Mendel and Wegener, they were premature science precisely because they introduced substantial novelty simultaneously in two of those facets.
Which made them too disruptive.
Way too disruptive for the reigning paradigm.
So if premature science is novelty in two facets, where does that really dismissive label, pseudoscience, fit into Kuhn's model?
Well, under this interpretation, pseudoscience is often defined by just wholesale cutting loose from all three established aspects: theory, data, and method. A complete break from the accepted paradigm. However, and this is a vital nuance that has to temper our judgment, the source notes that valid, even foundational knowledge might sometimes result even from this deepest level of novelty.
Like what?
The historical example is natural history, which was largely developed ab initio from scratch, without existing models, and yet it still formed the basis for modern biological science.
This inherent ambiguity is why we have to be so careful with these labels. If the line is constantly shifting, calling something pseudoscience is rarely a permanent or, an objective conclusion.
That's exactly right. The failure to find these clear-cut distinctions is, as the source says, well-nigh preordained, because the practices of successful science are so varied and the pace of discovery is just so unpredictable.
And we have recent examples.
We do, concrete ones. Acupuncture was generally despised and dismissed by Western medical science until the 1970s. Ball lightning was dismissed by many meteorologists as an optical illusion or a myth until, recent decades when physicists began studying it in detail. The moment we try to use a label to permanently close a field of inquiry, we risk repeating the exact same mistakes made with Mendel and Wegener.
That sets the stage perfectly for our central term today: pathological science. This wasn't coined by some skeptical philosopher, was it?
No, not at all. It was coined by one of the most distinguished scientists of his time, the Nobel Prize winner Irving Langmuir, in a very famous 1953 talk. Langmuir, a brilliant physical chemist who worked at GE, he synthesized his observations from decades of reviewing controversial claims. He called it the science of things that aren't so, and he provided a canonical definition that is, still used to blacklist research today.
And he intended it as a diagnostic tool.
A rigorous one, to protect the scientific community from, self-deception.
He laid out 6 characteristics for what constitutes pathological science. Let's list them. Because on the surface, they sound very intuitive and very precise.
They really do. First, he noted that the magnitude of the claimed effect is substantially independent of the intensity of the thing causing it. You push harder, but the result doesn't get any better.
Okay, that's one.
Second, the effect is always close to the limits of detectability. It often requires vast, complex data processing because the statistical significance is so low.
Number 3.
Third, there are often claims of enormous accuracy, way beyond the precision of the actual measurement device. Fourth, the theories put forth to explain the effect are fantastic and contrary to existing experience.
Okay.
Fifth, criticisms or failures to replicate are met with ad hoc excuses. And finally, the ratio of supporters to critics rises quickly, peaks around 50%, and then gradually falls to oblivion, like a fad.
It's a seemingly perfect checklist for identifying suspect research. It hits all the notes. Poor data, excessive claims, defensive rationalizations. But here is the central, devastating insight from our sources. Langmuir's criteria are actually non-functional for distinguishing good science from bad. So what's the first major crack in that foundation?
The first crack is realizing that the criteria are just too broad. They identify controversy and novelty, not necessarily pathology. The historian of science, Richard Rhodes, pointed out that Langmuir's 6 measures fit the initial discovery of prions perfectly.
The discovery for which Stanley Prisner received a Nobel Prize in 1997.
Exactly. Prions were initially a fantastic theory contrary to experience, right? The idea of an infectious protein with no nucleic acid.
It broke all the rules.
It violated the foundational dogma of biology that all infectious agents have to have DNA or RNA. That fits criterion 4 perfectly, a fantastic theory.
And when people couldn't replicate his findings.
When they couldn't immediately replicate his findings, he often offered ad hoc explanations about differences in purification methods or unique strain variations. That fits criterion 5. And yet, the work was correct, it was transformative, and it earned a Nobel Prize. The sheer fact that a set of measures designed to detect things that aren't so can perfectly describe a verified Nobel-level breakthrough proves the criteria are fundamentally flawed.
And we can see this problem even when we look at fields we consider the pinnacle of modern rigor.
Absolutely. Think about high-energy physics, searching for the Higgs boson or other exotic particles. They rely on vast computer manipulation to remove background noise and isolate these fleeting events that are, by definition, near the limits of detectability.
So that's criterion 2 right there.
Perfectly. The whole enterprise is often about detecting effects just above the noise floor. Now, consider modern cosmology. Theories like the Big Bang, dark matter, black holes, and especially string theory.
Fantastic theories contrary to experience. Criterion 4 again.
Precisely. We can't perform experiments on the Big Bang. We're relying on indirect evidence and models that put forth concepts, like 95% of the universe being composed of stuff we can't even detect, that are entirely contrary to our everyday tangible experience.
Right.
Yet these are foundational theories of modern physics. And what's more, Licata showed that criterion 5, the use of ad hoc modification. The excuses, like adding an extra dimension in string theory or postulating a new flavor of neutrino when the model fails, that's actually characteristic of regular progressive science. It's how you maintain the core theoretical structure while modifying the smaller beliefs.
So the criteria don't identify bad scientists. They often identify revolutionary or frontier or just methodologically complicated science, a crucial distinction. Let's look at the 2 classic case studies Langmuir himself cited. First, N-rays in France, early 20th century.
René Blanlot, a highly distinguished French physicist, he announced the discovery of N-rays named after the University of Nancy. He claimed this was a new form of radiation emitted by, well, living bodies, metals, flames.
It sounds plausible enough, like an exotic extension of things like X-rays.
It was, and the initial acceptance was wide. I mean, scores of French scientists published literally hundreds of papers confirming these findings, often in prestigious journals.
But the detection method was the problem.
It was highly subjective. In a darkened lab, researchers used a measuring scale with spots of light that were said to get brighter when N-rays were present. The key was the visual observation of these tiny variations in intensity.
And the scientific community outside of France just couldn't reproduce it.
They struggled mightily, which eventually led to the famous debunking. The American physicist Robert Wood was sent to investigate. He visited Blondlot's lab, which was, completely darkened for the measurements.
Right.
Wood watched as Blondlot conducted his experiments, measuring the supposed refraction of the N rays after they passed through an aluminum prism. And then, crucially, without Blondlot noticing, Wood surreptitiously reached over
and pocketed the prism.
removed the aluminum prism, the very thing that was supposedly refracting the rays, and slipped it into his pocket.
And the measurements just continued.
The measurements continued unchanged. Blondlot and his assistants reported the same fluctuations, the same degree of refraction, completely convinced the light spots were brightening and shifting. Wood declared it an optical illusion, a mass hallucination based on expectation bias.
Which is just utterly devastating. But the irony here is what saves Blondlot's reputation from the charge of, simple incompetence.
The irony is incredible. Blondlot was previously lauded by the scientific community for establishing that X-rays moved at the speed of light. And he did that using the exact same method.
Visual observation of intensity variations.
The exact same method. He was merely continuing a successful technique in a time before we had high-fidelity sensors. As one scholar noted, the N-rays affair was a sort of mass hallucination proceeding from an entirely reasonable beginning. His mistake wasn't willful fraud. It was relying on a method that was adequate for one thing, X-rays, but totally insufficient for something far more subtle.
Let's move to the second classic example, polywater, from the late 1960s. This case hinges not on visual illusion, but on undetectable contamination.
Polywater. This involved Russian scientists Fedyakin and Durjagin. They observed anomalous properties in water that had been condensed in extremely narrow capillary tubes.
And what were they reporting?
They reported water with a 40% higher density than normal, drastically different boiling and freezing points, weird viscosity, truly anomalous stuff.
The discovery was so shocking that it quickly gained global acceptance.
It really did. Scientists worldwide scrambled to reproduce it and investigate it. The famed British physicist J.D. Bernal, a leading figure in materials science, called polywater the most important physical-chemical discovery of this century.
Wow.
It became the center of discussion at prestigious Gordon research conferences. That signals a very high level of institutional trust.
So what was the reality behind the anomaly?
The reality turned out to be contaminated water, specifically water that had dissolved trace amounts of organic material and silicates from the air or the tubes themselves. But, and this is the critical defense against the pathological label, the impurities responsible were below the level of detection by the spectroscopic methods they had available at the time.
So the contamination was real, but the techniques they had access to couldn't prove it was there.
Precisely. The Russian workers had specifically used high-purity quartz tubing, which was the established, reasonable practice for a high-purity experiment. When the first major American publication on polywater came out, the authors actually emphasized the lack of spectroscopic evidence of contamination.
Which lent credence to the whole thing.
Of course. The scientific community later accused the researchers of sloppy technique, but the evidence shows they followed the best available methodology. Their failure was a methodological ceiling imposed by 1960s technology, not scientific misconduct.
This brings us to a foundational conclusion then. If the researchers in N-rays and polywater were using the same practices that led to their praised work, and their failures were due to methodological limitations or psychological bias, then accusing them of scientific misconduct doesn't really seem justified.
It's absolutely not, and the sources make a crucial argument here. Objectivity in science. It's achieved through mutual critiquing across a broad community. It's not something that's guaranteed by the individual practices of researchers, even Nobel winners.
Right.
So calling these episodes pathological science is therefore an unhelpful, aggressive epithet. It's better understood as a term we apply to potentially revolutionary discoveries that did not pan out, or where the initial methods were just insufficient. And this distinction is vital when we turn to cold fusion, which was thrown into this same dustbin within 40 days of its announcement.
Okay, let's pivot to the modern case study, which exploded onto the scene with unprecedented media attention in 1989. This is the moment when the electrochemists Martin Fleischmann and Stanley Pons F&P claimed they had achieved nuclear fusion at room temperature.
The initial announcement in Salt Lake City was incredibly dramatic. It generated media expectations that bordered on hysteria.
Unlimited, cheap, clean energy.
From a tabletop device, yeah. Their experiment involved a seemingly simple setup, a palladium metal electrode submerged in heavy water, or D2O. They claimed to have produced excess heat energy that just couldn't be accounted for by any known chemical reaction or stored energy, which suggested a clear nuclear origin.
But the immediate reaction from the global mainstream, particularly from high-energy and nuclear physicists, was swift, brutal, and utterly dismissive.
Within about 40 days, before rigorous investigations could even be properly initiated, the claim was comprehensively dismissed by the mainstream scientific community.
And their objection was twofold.
Twofold and fundamental, resting on established nuclear theory. First, F&P themselves noted they did not detect the classic DD fusion product, helium-3.
Okay.
Second, and most critically, they lacked the lethal, high-energy neutron and gamma-ray signatures that conventional DD fusion should produce, given the amount of heat they were claiming.
So the physicist's logic was, the heat is there, but the expected radiation isn't.
Therefore, the heat must be an artifact of some chemical error, and they slapped the label pathological science on it.
The scientific community prioritized defending existing theory over patient investigation. Our sources argue this rapid rejection was a systemic failure of due process.
It was, and it fundamentally stalled the field for 3 decades. The core problem was a disciplinary disconnect. F&P were electrochemists. They specialized in materials science, electrodynamics. Their primary critics were nuclear physicists, who were operating under the fundamental assumption that fusion requires millions of degrees Kelvin.
And they wouldn't budge from that.
The physicists prioritized the absolute defense of established nuclear theory over any kind of interdisciplinary investigation of these anomalous empirical observations. This failure of intellectual flexibility, which, some see as academic arrogance, is the primary cause for the delay.
Wait, let me challenge that for a moment. If the nuclear physicists' fundamental theory, the Coulomb barrier, which we'll get to, if that was sound, isn't it scientifically responsible to dismiss claims that violate it? Where do you draw the line between intellectual flexibility and just protecting the community from obvious, crackpottery?
That's a necessary question, but the line is drawn not by theory, but by patient empirical verification. A sound scientific approach should have been skeptical, yes, of course, but it also should have been intensely curious.
Okay.
When F&P claimed anomalous heat, the correct scientific response shouldn't have been instantaneous dismissal. It should have been massive investment in diagnostics and multidisciplinary teams to try to replicate the anomaly and verify the products.
Instead, they just declared it was a mistake.
The physicists declared the heat was chemical and the observation was mistaken because it violated their theory without first rigorously proving the absence of any nuclear ash. They failed to acknowledge that the solid-state environment of the palladium lattice might introduce a new variable that their plasma physics models just didn't account for. It was methodological conservatism masked as a theoretical defense.
The societal consequence of this reaction is arguably even more damaging than the initial scientific error. This crisis didn't just kill the research, it created what our sources call the reputation trap.
The reputation trap. It's the sociological concept that cold fusion became tainted and contagious. Any scientist associated with it was deemed suspect.
So respectable scientists just stayed away.
Outsiders, respectable scientists in established fields who weren't already involved avoided the topic entirely. Why? Because they feared that taking the subject seriously, or even just demonstrating an open mind in a funding application or a university seminar, could contaminate their entire careers. The threat was professional exile. As one researcher vividly described the environment, if there's something scientists fear, it is to become like pariahs.
This sets up a vicious, circular logic that's protected by a mask of respectability.
It's a self-sustaining intellectual echo chamber. A new lab might produce results indicating excess heat and helium-4, but those results are ignored by funding bodies or major journals because they concern cold fusion.
And why is cold fusion ignored?
Because it's known to be pseudoscience. And why is it known? Because the initial attempts at replication failed 25 or 30 years ago, and the field has a terrible reputation. Scientists were actively discouraged from pursuing a low probability, extremely high impact possibility due to social, financial, and reputational norms, not because of pure empirical disproof. This is the definition of institutional intellectual rigidity.
The cost of that conservatism, if this technology is real, is immeasurable. A wasted generation of clean energy progress.
That's the strategic consequence. We saw earlier that the cost of a false negative, wrongly dismissing a transformative technology, can be far higher than the cost of a false positive, funding a few dead ends.
Right.
When a technology promises to solve global energy and climate challenges, the institutional conservatism that prioritizes career safety over intellectual risk-taking becomes, paradoxically, pathological to progress itself.
Now, we need to address the physics objection head-on, because it's the strongest argument for the dismissals back in '89. The fundamental physical argument against cold fusion is the Coulomb barrier. Let's start there. What is it, and why does it make fusion at room temperature conventionally impossible?
The Coulomb barrier is the enormous electrostatic repulsion that exists between any two positively charged atomic nuclei.
Like charges repel.
Exactly. In the case of deuterium fusion, you have two positive deuterons. For them to fuse and release energy, they have to get incredibly close within about a femtometer, or 10 to the minus 15 meters, for the strong nuclear force to take over and bind them together.
And pushing them that close requires overcoming a monumental repulsive force.
Monumental. To overcome that repulsion classically, you need immense kinetic energy to just ram them together. And since temperature is a measure of kinetic energy, the calculation shows the barrier requires temperatures on the order of millions of degrees Kelvin.
That's the core of the sun.
Or the conditions inside a massive pulsed hot fusion reactor like a tokamak. The kinetic energies available at room temperature, which is only a few hundred Kelvin, are vastly, impossibly too low for thermal fusion, according to classical physics. This is why the physicists were so confident in their dismissal.
So if it can't be done thermally, the only way around it is the accepted quantum mechanical loophole.
Correct. The only accepted low-energy mechanism is quantum mechanical tunneling, or gamma tunneling. In quantum mechanics, particles behave like waves. That means there's a small, non-zero probability that two nuclei can tunnel through the repulsive energy barrier, even if they don't have enough classical energy to jump over it.
But they still need to get extremely close.
That's the key. For this probability to become meaningful, the nuclei still need to get extremely close to each other.
And we do have one accepted physical example of cold fusion in the books, which is muon-catalyzed fusion, or CF. This serves as the benchmark for any theoretical defense of LENR.
Muon-catalyzed fusion is a robust, verified phenomenon. It demonstrates that fusion can indeed occur at ambient temperatures. It works because the electron that orbits the deuterium nucleus is replaced by a muon.
Which is much heavier.
Much heavier. The muon has the same negative charge as an electron, but it's about 200 times more massive. Because of this high mass, the muon pulls the two positive deuterium nuclei incredibly close together.
It shrinks the atomic orbit dramatically.
Yes. The orbit is shrunk so much that the two deuterons are physically near enough to significantly enhance the probability of quantum tunneling, and that leads to fusion. It's a physical solution to the Coulomb barrier problem.
But it's not a source of energy.
Not at all.
Yeah.
As we mentioned, it's non-viable as an energy source because the energy required to create the muons in the first place far exceeds the energy released. But this sets the definitive challenge for LENR. It has to provide a barrier suppression effect that's equivalent to that heavy exotic muon, but at a negligible energy cost, using only the low-mass electron cloud that's already in the material.
Okay, moving now to the experimental side. The field has been plagued by a chronic reproducibility hurdle. This is what feeds the skepticism. The results are inconsistent, suggesting it might all be random noise.
The sources absolutely confirm that this inconsistency has been the central, enduring challenge of the field. It suggests that key control variables or triggers remain elusive and uncontrolled. However, extensive analysis conducted after the initial failures points to one necessary, though still insufficient, condition: achieving a high deuterium loading in the palladium lattice, specifically a deuterium to palladium ratio of 0.85 or higher.
So the metal needs to be absolutely saturated with the fuel for anything interesting to happen.
Precisely. If that ratio isn't consistently achieved, and controlling that is a massive materials science problem involving impurities, surface conditions, current density, then the experiment just won't work. The early replication failures were likely due to the inability of other labs to precisely control this high loading condition, which reinforced the view that the original FMP results were spurious. The problem was methodological control, not fraud.
This brings us to the critical modern empirical breakthrough that fundamentally refutes the historical dismissal: the correlation between excess heat and a specific nuclear product.
This is the hard evidence. This is what has forced governments and major institutions to re-engage. The strongest modern case rests on the measured correlation between the production of excess heat and the presence of helium-4.
Helium-4, okay.
Reputable, independent institutions like SRI International have corroborated a clear relationship between the measurements of excess heat and helium-4 production.
And tell us about the reaction itself and the energy involved.
This correlation strongly suggests the dominant reaction in the solid-state environment is D plus D goes to helium-4 plus energy.
D plus D.
Deuterium plus deuterium. Crucially, this reaction releases a substantial amount of energy, approximately 24 MeV mega electron volts per single fusion event. This thermodynamic correspondence is the smoking gun. If you measure an anomalous amount of heat and you find a proportional amount of the nuclear ash, the helium-4, you have empirical proof that a nuclear process is occurring.
And this solves the core paradox of 1989. If nuclear fusion was happening, why weren't Fleischmann and Pons killed by lethal gamma rays and neutrons?
Exactly. The correlation suggests the fusion is aneutronic.
Meaning without neutrons.
Without neutrons. The modern hypothesis is that the 24 MeV of energy released during the fusion event is not expelled violently as high-energy radiation, but is transferred directly, gently, and efficiently to the palladium lattice as heat. The solid-state environment, acting as an extremely dense matrix, essentially absorbs and thermalizes the energy almost instantaneously, which suppresses the emission of high-energy gamma rays and neutrons.
So the palladium lattice is essentially acting like a big, dense nuclear sponge. It's absorbing that 24 MeV of energy and preventing the violent explosion we'd expect in, say, a plasma fusion device.
That is the perfect way to visualize it. It absorbs the energy and converts it instantly to thermal energy. The finding of this thermodynamic correspondence between heat and helium-4 is the ultimate vindication. It fundamentally refutes the historical designation of LER as pathological science. The failure in 1989 wasn't a failure of physics, it was a failure of diagnostics. They were looking for the wrong energy products using the wrong tools. They were expecting neutron splatter, but the effect was only visible as heat and helium ash.
Given that empirical refutation of the pathology label, the focus has entirely shifted to how the solid-state lattice enables this process. And this means we're now seeing major institutions like NASA and ARPA-E providing advanced theoretical frameworks, moving away from just looking at anomalies. Let's start with NASA's work on lattice confinement fusion.
Right. NASA, primarily through the Glenn Research Center, is researching lattice confinement fusion, or LCF. The goal is to secure a compact, new energy source for long-duration deep space exploration.
And the theory.
The LCF theory is complex, but the core idea is that the metal host, often a palladium-silver alloy, is not just a passive vessel for the fuel, it's an active participant.
How does the metal structure actively participate in creating fusion conditions?
It's all about geometric and electronic manipulation. The crystal structure of the metal is theorized to confine the fuel nuclei, the deuterium, into these linear defects within the lattice. You can think of them being squeezed into high-density lanes.
Right.
This physical confinement forces the deuterons into far closer proximity than would ever be possible in a gas or a plasma.
And that closeness is supported by the electronic structure of the metal itself.
Precisely. LCF theory emphasizes the role of the metal's high density of free electrons. These negative charges screen the positive charges of the deuterons. This electron screening dramatically reduces the powerful electrostatic repulsion, the Coulomb barrier, which significantly increases the likelihood of quantum tunneling at ambient temperatures.
So it's a form of materials engineering.
Highly advanced materials engineering, aiming to create a microenvironment that replicates the effect of the heavy muon, but just using the material's own electrons.
And what's fascinating here is that mainstream theoretical physics is now supporting this idea of enhanced electron screening, which lends enormous credibility to the whole enterprise.
Yes. Theoretical physicists are using state-of-the-art computational tools, specifically density functional theory, or DFT codes. DFT is the gold standard in computational materials science for modeling quantum mechanical effects inside a solid.
And what did they find?
They found that the electron density in deuterated palladium can be massive. It can exceed 10 to the 23rd electrons per cubic centimeter.
Why is that number so significant? And why is the use of DFT so important for bridging this gap?
The use of DFT as a bridge because it's a standard, non-controversial tool used by every respectable physics and chemistry department in the world.
Okay.
The calculations show that this incredible electron density creates conditions for what's called Fermi-degenerate strong screening. This is a state of matter that's similar to what occurs in the core of white dwarf stars. And in these ultra-dense environments, fusion can occur at low temperatures.
So they're using standard theory.
By applying standard theory to the solid-state environment, mainstream physicists have created a theoretical mechanism that could allow LENR to exist without violating known physics. It just shifts the context.
This convergence of empirical evidence, the heat and helium-4 and advanced theory, LCF and DFT, is what paved the way for the most critical institutional commitment. The U.S. Department of Energy's Advanced Research Projects Agency, Energy, or ARPE. They're putting serious money into this.
ARPA-E has committed up to $10 million for an exploratory topic focused entirely on LNR. This is a classic high-stakes risk management strategy. They acknowledge the historical stalemate. Lack of funding prevented the rigorous evidence needed for future funding, which created the perpetual reputation trap. Their strategy is designed to break this vicious cycle.
What exactly is ARPE's specific goal? They aren't trying to commercialize it yet, right?
No, the goal is purely scientific verification, designed to close the file. They are soliciting hypotheses-driven approaches toward realizing diagnostic evidence of low-energy nuclear reactions that are convincing to the wider scientific community.
And the mandate is specific.
Highly specific. Establish at least one on-demand, repeatable LNR experiment. This investment is designed to close the case permanently, either by providing irrefutable third-party repeatable proof or by providing such rigorous, non-viable evidence that it prevents any future public expenditure on non-starter concepts.
And they've engineered a way to bypass the reputation trap within the research teams themselves, forcing the very collaboration that was missing back in 1989.
That is the genius of the ARPE strategy. They require interdisciplinary teaming. They are actively facilitating collaboration between longtime LENR researchers who have the specialized knowledge of how to create the effect and external nuclear diagnostic experts who are skeptical but highly rigorous third-party verifiers.
So it forces the two sides together.
This requirement ensures that rigor is injected, external verification is built in, and the historical disciplinary gap between electrochemists and nuclear interpreters is bridged. It's an institutional acknowledgement that the failure of 1989 was, at its heart, sociological.
ARPE is betting on a low-probability, high-impact outcome. For a fraction of what they spend on one massive hot fusion project, they might solve, 50% of the global decarbonization problem?
That risk profile is immensely appealing and politically necessary. But they aren't alone. Google also funded a massive, multi-institutional, high-rigor reevaluation. They spent about $10 million since 2015.
And what did they find?
They publicly stated that while they found no conclusive evidence of the effect they were looking for, their investigation yielded profound new insights into highly hydrated metals and low-energy nuclear reactions. And this led them to conclude critically that there is still interesting science to be done. They legitimized the materials science.
And we see the government labs, specifically the Navy, stepping in, citing the advantage of working outside the typical academic environment.
Yes, scientists at the Naval Surface Warfare Center pulled together a collaboration with other government labs, including the Army and NIST. They explicitly noted that government labs have more freedom to pursue a controversial topic because their career path is less dependent on external grant review boards and academic peer reputation than a university professor's is.
It's a dedicated attempt to settle it scientifically.
Free from the reputation trap.
Japan, too, has a mixed history here.
They do. They had a costly failure with their $20 million government MITA program from 1992 to 1997. It failed to achieve repeatability and was terminated, which shows the risk is very real. However, even Japan restarted research in 2015 through the NIDO program, focusing again on nanometal hydrogen energy systems. It shows the persistent geopolitical interest in this potential technology.
Finally, we should look at the claims coming from the private sector, specifically Brillouin Energy, because they are claiming they've achieved total control.
Right. Brillouin Energy claims to be far ahead of the public research level. They've developed a system called the hydrogen hot tube, or HHT. They claim it consistently demonstrated the key performance trifecta of net positive power out of the wall, steady-state operation, as measured by heat and water.
And this is verified.
They assert this has been verified by independent third parties, including SRA International. But their most significant claim, the one that makes them unique, is that they have a control switch.
A control switch.
One that allows them to turn the LENR heat generation reaction on, UP, down, and RFF reliably, 100% of the time. If that's true, it eliminates the biggest historical hurdle, lack of control and repeatability.
The Brillouin claims bring us directly to the enormous gap between commercial rhetoric and scientific reality. We have to weigh the strategic appeal against the technical risk. First, let's quickly summarize the transformative potential that justifies this institutional pivot and these aggressive private sector claims.
The strategic appeal of LEN is almost unparalleled in the energy landscape. Proponents claim it could be the lowest cost of all commercially available energy sources.
Wow.
The fuel, deuterium, is widely available in normal water and is non-radioactive. The systems don't require the extreme conditions of hot fusion or fission, making them inherently safe and localized. And crucially, they produce little to no long-lived radioactive waste.
And in the context of global decarbonization, the implications are just staggering.
Absolutely. We're talking about a source that can produce intense carbon-free heat, which is essential for heavy industrial processes. This potential contribution to decarbonizing industrial heat and transportation sectors, which combined account for about 50% of global CO2 equivalent emissions, is why IRPA used this as a strategic imperative. Their other programs are struggling with deep decarbonization challenges.
Give us a taste of those other ARPA-E challenges just to frame the stakes here if LENR fails to deliver.
Sure. Look at their locomotives program, which is modeling decarbonization for rail freight. It's targeting a reduction of 40 million tons of CO2 per year using entirely new energy storage systems, a monumental engineering effort.
Okay.
Or their ROSI program, which aims to revolutionize iron making to achieve zero direct process emissions in the steel industry. These are incredibly difficult, costly problems requiring very specific technological solutions.
And LENR could be a silver bullet.
If LNR is real, it offers a single, universal, distributed heat source that could immediately service all these industrial needs, eliminating the need for these massive, hyper-specific engineering interventions. The global stakes are that high.
But the reality is that right now, commercial players are claiming they are ready to sell, while major institutions are still trying to prove the fundamental science. This is the TRL disparity, the technology readiness level gap.
And this disparity constitutes an extremely high strategic risk. When private companies like Brillouin claim rapid commercialization, they are implicitly claiming a technology readiness level of 6 or 7. That means they have a working prototype validated in a relevant environment.
But the institutional review says otherwise.
The institutional review from ARPA-E and Google confirms that technology fundamentally resides at TRL2 concept formulation, or TRL3 proof of concept.
Why is the scientific TRL still so low, despite the positive evidence of heat in helium-4?
Because the core scientific principles, specifically the repeatable on-demand production of the heat coupled with the helium-4, are not yet consistently proven on an engineering scale. We know it can happen under specific, still mysterious conditions, but we don't yet know how to force it to happen predictably and sustainably 100% of the time in a device that can be scaled up.
So until ARPA's mandate is met.
Until there's one repeatable experiment, the technology remains firmly in TRL3 territory.
So investors jumping in based on TRL 6 to 7 commercial hype when the underlying science is still stuck at TRL 2 or 3 are facing an extreme risk of failure.
An existential risk. Private investment has to be contingent on achieving the high scientific standards that ARPA-E is seeking, that verifiable, repeatable heat and helium-4 correlation, rather than simply funding premature prototypes. If a commercial device fails due to scientific non-viability, it risks repeating the 1989 crisis on a massive scale, delegitimizing the field, and potentially killing the chance for genuine progress for another generation.
So the sources essentially advise that capital should be directed towards solving the TRL 2-3 problem first, understanding the basic physics, the lattice mechanics, the control variables, before scaling up the engineering.
That is the only defensible path forward. The focus has to be on advanced materials characterization and the use of tools like DFT to engineer specific lattice structures and electron densities that optimize the conditions for barrier suppression. This strategic long-term approach views LENR not as a quick commercial exit, but as a multi-decade bet on foundational quantum physics that has the potential for truly transformative global impact.
We have covered a huge amount of ground today, tracing the path of a concept from a philosophical argument about why science dismisses novelty, to a 3-decade exile, and finally to a high-stakes multi-million-dollar government investment designed to finally settle the debate.
What this deep dive shows is a critical dual narrative. On one hand, you have the profound philosophical risk of discarding science too quickly due to intellectual rigidity or, reputation fear. The idea that the accepted rules of normal science are simply inadequate for truly revolutionary breakthroughs. On the other hand, you have the modern strategic imperative to revisit cold fusion LENR due to its profound energy potential, driven by the realization that we desperately need carbon-free energy miracles to address climate change and industrial needs.
So where does the controversy stand now? Is it still about whether cold fusion is pathological or pseudoscience?
No, that language is now historical noise. The debate is now squarely focused on whether the conditions necessary for low-energy nuclear activity can be reliably, affordably, and predictably engineered within a solid-state lattice. The goal is clear. Use 21st-century diagnostic tools, particularly the high-fidelity measurement of helium-4 correlating with excess heat, to overcome the 20th-century methodological and sociological flaws that killed the field 3 decades ago. The scientific community is finally engaging in the necessary, rigorous, high-risk work, recognizing that the potential reward outweighs the historical stigma.
A profound shift in scientific courage. Now, for you, the learner, we spent a whole section looking at the stakes, the 50% of global CO2 emissions this could potentially solve. We've seen that the cost of a false negative, wrongly dismissing a transformative technology, may be far higher than the cost of a false positive, funding a dead end. The world needs energy miracles. So given this history of the reputation trap, and knowing the institutional and social forces that protect scientific consensus, what other black sheep of the scientific family, currently stuck outside the consensus due to historical dismissal, might offer the world the energy miracle or climate lifeline it desperately needs? That's your homework to explore.